Okay. Um, Before we get too far into your research, I did want to ask you, I often talk to people who are doing things that don't necessarily have immediately practical use. I've talked to several different people that are doing work on the gut microbiome, and it's kind of more research phase rather than, functional use phase. Um, why did you decide to do something that's more like functional based versus just say, man's search for knowledge?
Right. So because I was a mediocre athlete, I wanted to know why I was mediocre. A lot of people in exercise physiology started out as good athletes.
Okay.
You know, like we're good athletes, we're not great athletes. We wanted to be great athletes, so we're trying to figure out why we weren't great athletes.
Okay.
And so, I also was a strength coach at Michigan. So, and we would put the football players onto these strength programs. You would see some just they would blow up by like a balloon and they would get hugely strong, and other guys would do the same training program, but they would have no visible change in muscle mass, and their strength wouldn't go up dramatically. And
Hmm.
so part of the question that I had was, why are all these things happening? What is it about our bodies that allow us to adapt to these stimuli, these nutritional or these exercise based stimuli that make us bigger, stronger, or make us more endurance related? What are the things that those our exercise and our nutrition are actually doing? Because once you know that, if I know exactly which molecule my endurance exercise is turning on,
Hmm.
now what I can do is I can look for different ways that I can turn it on. So
Okay.
the perfect example is strength training. When we do strength training, you lift weights and you do sets and reps and you do a load. When I look at strength training, I'm seeing that the goal of strength training is to activate a specific kinase, and it's called the mammalian target of rapamycin. And so this protein is a single protein that we had shown that when you activate it, you get bigger muscles. You then take that together. So we've identified a single protein. And now what you do is say, all right, how can you activate that? Oh, look, amino acids activate mTOR. Oh, so then if we did strength training with amino acids, now we can get more from our strength training.
Hmm.
And sure enough, you get a bigger, stronger muscle when you do that. So if you understand the molecule that your exercise is turning on in order to have the positive effect that you want, now what I can do is I can figure out two or three different ways that I can activate that, or I can block an inhibitor, or I can do all of these different things so that I can get more from the same amount of exercise than somebody else would.
Okay. Are you only looking at like, I guess I'll say, physical ways to manipulate it, or are you also looking at like pharmacological ways to manipulate these different
So
things?
we've done it in a bunch of different ways. So I'll give you an example of how it would go. So we're studying muscle growth, and muscle growth is something that is it's harder to do when you're in a caloric deficit. And
Hmm.
so there's proteins that are activated by a caloric deficit. And so we worked with an animal that was a transgenic animal. It was a knockout animal, so it doesn't have that one of these proteins. And sure enough, when we did an overload, so a load designed to make the muscle grow bigger,
Hmm.
if the animal didn't have that protein, it actually got a significantly bigger muscle from the same exercise as its litter mate that did have that protein. And so then what we do is we go and we say, okay, so when you inhibit this, you get a bigger muscle. We go to the literature, there's a drug that can inhibit that. So
Hmm.
all we do is now inject every day. We injected the animals with the drug while they were going through the overload. Sure enough, they got a 77% greater muscle hypertrophy than the ones that were injected with saline.
Hmm.
Then you say, okay, now we know that this is working. So now let's look for natural products that can inhibit that same protein. And we found a bunch of natural products that inhibit the protein. We combined three of them. And now we've done a study where all we do is we feed animals those three natural products. We do the overload. And now instead of about 15% hypertrophy, which is what we would see in an animal that would get saline or salt water,
Hmm.
when we give those three natural products, we get a 65% hypertrophy. So
Okay.
we're getting a big, big increase in the amount of muscle growth from the same exercise stimulus. So that's kind of how we would do it, is we'd go and we'd look for specific things that are controlling or regulating, decreasing. And then what we do is we find, how do we get around these? Because a lot of things that we're trying to do is to overcome evolution. Mm-hmm. We evolved to be endurance athletes. We didn't evolve to have huge muscles and lots of strength. We're relatively weak relative to other animals, but we're really good at endurance. So if you're trying to grow muscles, you have to overcome the evolutionary pathway that we took, which was to become better endurance athletes. Mm-hmm. And so as you do that, what you're doing is you're having to figure out where those roadblocks were put up in order to make your muscles bigger. By finding those and then targeting them individually, you can actually see if you can get bigger muscles from the same exercise.
Okay. So it's kind of like I guess I'll say almost a stair step of isolating the mechanism, figuring out, it seems like you said, it's like using like some kind of drug to inhibit whatever you don't want activated, and then moving from there to more natural methods to achieve the same outcome, at least in your example.
So go ahead and go back to where you said it's a stair step of isolating.
So it's okay. So it seems like it's a stair step of like, okay, first it's research phase in terms of what mechanisms are actually active in this particular scenario, whatever we're studying, and then figuring out how can we, either enhance or inhibit whatever mechanism that is good or bad through, pharmacological means, and then stepping from there to, can we manipulate it with, I'll say like an apple or something, a natural product is what you said.
Foods, yeah.
Right. So it's like this whole process from just figuring out from I don't know anything to, okay, what's going on, and then taking those small steps all the way to, okay, this is the most effective way to do this without, injecting yourself with a drug.
Exactly. So what you're looking for is, the reason that we do it is because, look, it's hard enough to get people to exercise. Mm-hmm. If they don't get any response from the exercise, they're not going to continue. Right. But if they suddenly say, oh, wow, look at how I'm getting a big effect, and they see their body changing, they see these things changing within them, they're much more likely to continue to exercise. Mm-hmm. So if you can do the exercise and pair it with something that's not harmful, that could promote them or let them do more of it, or let them see that they're getting better at it sooner, that's a spectacular thing.
I kind of want to jump to a little bit specific question about mTOR, sure, which you had discussed on a different show. Again, just in case I'm off the wall, feel free to just slap me and say I don't know what you're talking about. So I think I understood you're at the time you were talking about like through exercise activating mTOR to create muscle growth, and how that can possibly inhibit its activation in other things like organ tissues like liver. Mm-hmm. Is that correct?
Yeah.
When I heard that, it made me wonder about, I think you also mentioned in another talk about being active helps increase people's lifespans. And I was wondering if this kind of inhibition in those organs and then promotion in the muscles is possibly like a cofactor for an increased lifespan, thinking about like cancer risk reduction and things like that.
Sure. So it's a great question. So the first thing is that 30% of all people who die from cancer die because of the muscle weakness associated. Because as the cancer gets bigger, it's going to need more amino acids, more nutrients to grow. And so it actually stimulates muscle atrophy. So it breaks down muscle in a process called cachexia. So there's great studies done by Stephen Blair's group that show that if you're in the strongest third of the population, you're 1/4 as likely to die from cancer. Mm-hmm. A lot of that's just because if you're stronger, you'll be able to survive the treatments, because the treatments are to put your body into poison. Mm-hmm. When you're doing strength training, one of the things you do is you activate mTOR, as I mentioned before. And mTOR is a protein that's important in growing cells. And so if you think of growing cells, that's great if you're talking about muscle. It's bad if you're talking about a cancer, because that's what a cancer needs to do to drive itself bigger. To make itself bigger, it needs to activate mTOR. And so what cancers are trying to do is they're trying to activate mTOR, and that's going to be important in growth. So when we do exercise that has a high metabolic cost, what we're going to do is we're going to have this tendency to decrease. Our whole body is now in what we call a caloric deficit. And when we're doing that, we're going to have this big stimulus to decrease the activity of mTOR in the tissues around the body. So that's one thing. So if you were to go out, even if you were to do endurance exercise and you were to run, say you're going to run for, you're going to go for an hour run. So you go out for your hour run, that's going to cause your liver and your fat cells and all these other tissues to have to change their metabolic state. Liver's got to produce glycogen or break down glycogen to glucose. It's got to regulate. While it's doing that, there's nice work that shows that as it does that, mTOR activity goes down. mTOR is inhibited when it's in this metabolic stress of exercise. Same thing is true in the fat cell. Same thing is true throughout the body, or in most of the body. Interestingly, in the brain, mTOR is activated by something called brain-derived neurotrophic factor, which is a growth factor that helps our brain continue to develop. And so one of the things that happens, that is purported to happen, is that as you exercise, you get more brain-derived neurotrophic factor, and that turns on mTOR in the brain. So locally in the brain, you're turning it on. In the liver, in the kidneys, in the fat, you're turning it off. And in the active muscle, if you're doing endurance exercise, you're going to decrease it a little bit. When you want to do strength exercise, we're going to increase it in the active muscles. And again, we're going to decrease it in the areas where all they sense is the stress, but they don't have the mechanical load that's going to give them the signal to grow. So what you're doing with exercise is you're modulating this. And then what we've recently realized is that that's the same thing you do with your diet. So we recently published a paper that showed that if you put mice onto a ketogenic diet, they live 13% longer than animals on a controlled diet. And the reason for this is that if as the animals died, we would do an autopsy or necropsy. And what we realized is that 8 out of 10 of the normal animals on a wild type chow, they die from cancer. When we open up the ones that die on the ketogenic diet, only 2 of those animals, 2 of the 10 animals we measured there actually died from cancer. And again, what you're doing on a ketogenic diet, you're removing carbohydrate. mTOR is stimulated by 3 things. The 3 things are load, and that's how we turn it on in our muscles, and then metabolism. And the two parts of the metabolism, one is the amino acids, specifically the amino acid leucine turns on mTOR. The second one is insulin. So if you have low insulin because there's no carbohydrate in the diet, you only have one of the 2 dietary stimuli for mTOR, so you don't turn on mTOR as much in those tissues. And then because you're doing exercise together with the amino acids, you're able to maintain the muscle mass. So you can turn the mTOR on in the muscle, but because you don't have the loading in all these other tissues, you don't turn on mTOR in the other tissues. So in the ketogenic diet, what we saw in these animals is that they had, as they got older, they had maintained their muscle function in age, they maintained their endurance in age, and we didn't see as many cancers in the non-muscular tissues.
So I know keto is very, very popular right now. And I've spoken to several different registered dietitians about it. Everybody seems to have a different opinion on it. I have kind of a 2-parter for you. I think in another interview that I listened to where the interviewer was asking you about mTOR and all these kind of things, and talking about, I think his question was, should we just try to get rid of inhibit mTOR entirely, which you've kind of already covered. But you explained how a large part of the increased lifespan in the mice is that 80% of lab mice die from cancer, and when you inhibit it, you inhibit the cancer. So part 1 of my question, I guess, is how do we avoid, obviously it's easy for you because it's your job and you're very well versed in dealing with these things, but how do we as kind of laymen avoid applying kind of, I'll say fallacies or fallacious arguments from lab research to real life? And
Right.
then is a ketogenic diet sustainable for, I guess I'll say, the majority of life, not just in a, I'll say,
Laboratory
like
setting.
laboratory setting or
Right.
like in a emergency cancer inhibiting kind of setting?
Right. So those are both good questions. So the first one is basically, do we want to inhibit mTOR all the time?
Right.
And the answer there is that the only drug that, or one of the best studied drugs that increases lifespan, again, in rodents, but it's also working now in dogs, is rapamycin, which is an inhibitor of mTOR.
Mm-hmm.
And again, it's decreasing cancer growth, and it's maintaining it, a lot of the functionality. When you then try and translate that into people, and that was one of the other things that you wanted to talk about here.
Right. Right.
Now what we have to do is we have to figure out, okay, how much of what we're seeing in animals is what we're seeing in people?
Mm-hmm.
So yes, only 20% of people die from cancer on average, whereas 80% of rodents die from cancer in the laboratory situation. So that's not necessarily going to be a direct comparison, because
Right.
if it's all about cancer, there's a lot of people who aren't going to die from cancer. So maybe they're not going to have as much of a benefit from keto. So what we're looking at here is a number of different things. So the first thing, when you're trying to decide whether something is good for a person, and you're reading stuff in the literature and says, oh, look, the increased lifespan in a rodent.
Mm-hmm.
What you have to do is you have to say, okay, are the same things that are killing the rodent killing me? If I have a family history of cancer, I might answer yes, because that's definitely something that I'm worried about. If I'm much more about cardiovascular, my family all dies from heart attacks. Now I'm got to mitigate that and say, well, maybe it's going to do something on the cancer front, but it might, it's questionable whether it has any benefit for me as somebody who's on who's got a more cardiovascular problem potentially. Mm-hmm. So that's the first thing to do. The second thing to do is to try and figure out how it's working and whether that's a good thing. All right. So when we talk about mTOR inhibition using diet, there's two ways to do it. You can do it either on a keto diet, which is to eliminate the carbohydrate component, mm-hmm. or you can do it on a low protein diet, which is to eliminate the protein component.
Right.
Both of those two things in laboratory or in research animals increase longevity. Both of them, if you look at them for humans, we know that in humans, the number one predictor of longevity is actually muscle strength. Mm-hmm. So your muscle strength at your midpoint of life is the greatest predictor of your longevity that we have. So if you're in the strongest third at 40, in your mid 40s, you're 2.5 times more likely to make it to 100 years of age than if you're in the weakest third. You're also, and it is strength specific, because if you're in the best aerobic fitness, if you're in the top third of aerobic fitness, only increases longevity by about 10%. Mm-hmm. So instead of 2.5-fold, it's 10%. So there is something about strength that's really good for longevity. So now if we say, okay, we're going to do a low protein diet to increase longevity, mm-hmm. well, that's going to cost me muscle.
Right.
And over time, that's going to potentially, in a human, not be beneficial. And it is one of the hardest things about any longevity studies, is that all longevity studies have to be done in a model organism. Mm-hmm. Because a longevity study follows people or follows organisms until they die.
Right.
I get, my grants are 5 years at the longest.
Yeah.
I am not going to be able to follow people until they die with a 5-year grant.
Right. It would have to be some kind of like lineage grant where like you start it, you do it for 20 years, then you hand it off to a student and then they do it for 20. Like it would be some kind of, there's a couple of studies that have done it. Like there's a Harvard longevity study, right,
where it's just Harvard has done it, or an organization like that, or a national organization. There's some studies on nurses in certain parts of the world. Mm-hmm. So you can do it. It's just really, really hard. Yeah. So the first longevity, a lot of the longevity studies were done in C. elegans, these little tiny worms. Mm-hmm. And then you say, oh, look at these great things. They increase lifespan. But what kills a worm is actually their intestine becomes permeable, and they they just basically take up bacteria and they get an infection and they die.
Okay.
That's not how most of us die.
Right.
So again, early research is done in worms. You can smile at that and say, okay, that's interesting, but don't change your behavior because of it.
Right.
As you go up in organisms, as you get into rodents, now you say, okay, that's interesting. They're increasing longevity. Is it just because they're getting rid of cancer? Mm-hmm. If it is, then maybe that applies to you and maybe it doesn't. But if they're not affecting cancer rate and they're increasing longevity, the next question to ask is if they're increasing health span. Health span is how long you live, but are still active. You can still do all of these things. You still maintain your strength and your endurance and your physical capabilities. And that's the next question. And that's where the ketogenic study that we did is interesting, because the animals on the ketogenic study maintained their muscle strength, their muscle size, and their muscle endurance as they aged. And we think that that's a result of mTOR again, but it's not all of the growth related. When you inhibit mTOR, what happens is, because mTOR is mostly on synthesis, when it's activated, it makes things. Mm-hmm. When you inhibit it, what happens is you increase the breakdown of things. Okay. And one of the things you increase breakdown of is mitochondria. And what you do is you take out damaged mitochondria. So any mitochondria that is damaged is going to go through what's called mitophagy, which is the process where we remove something like a mitochondria, a big organelle. And when we do that, now we've broken down these mitochondria that aren't working well. If we always have mTOR on, you're not breaking down mitochondria that are working poorly. Okay. So you get a bunch of mitochondria that don't work so well. You produce free radicals. You do all these other negative things. Mm-hmm. And as a result, your functionality goes down over time. So one of the other potential benefits of inhibiting mTOR is it, when you inhibit it, you turn over proteins faster. Mm-hmm. And when that happens, now you have newer proteins that don't have as many changes in them. And just like, if you go out and you're going to go out and shoot baskets like I did for years, mm-hmm. when you have the old net and you've shot thousands upon thousands of shots, it starts to wear. It starts to get frayed. It doesn't work as well. You put on a new net, now everything works well. It flows better. The whole system works the way it's supposed to. All we're doing as we do this is we're turning over the proteins so that the net stays new all the time. And that's really one of the key components of that type of situation. And I'm not a proponent, but I do the research, but I'm not on a ketogenic diet. What I do is I use exercise in the same way. Right. Because what we're doing is we're trying to inhibit mTOR locally, get turnover of protein at a higher rate, and all of those things I can do by doing endurance-based exercises. So you can do it in a variety of different ways. Mm-hmm. It doesn't have to be one thing, and there's not one magic pill that you got to do this because it's the best. Right. It's a combination.